I think everyone misses it. And but I think the hybrid model is kind of here to stay as well, because it allows so many other people to attend that wouldn't be able to because of distance and cost and things like that. So I think
Absolutely.
so I think we will be seeing the hybrid model for quite some time.
But
Anyway,
I gotta say, like, one of the things I miss most about events is like the feedback that you
yeah.
get just from talking to people after the talk. That like you get so much more feedback than you do now.
It's true.
Um,
It's true.
yeah,
It's true. And oftentimes, I think the best part of a talk is afterwards when you can go up to the speaker and say, like, "Hey, I noticed you
yeah,
mentioned this." Like, because sometimes you might not have enough time to get to all the questions. So I think that is true. And because online, it's just not the same.
yep, yep.
It makes some things easier, but other things more difficult. That's true. What was just out of curiosity? What was the last talk you gave was in PromCon?
Virtually, yeah.
Yeah.
So no, I was on the rule code last week.
Oh,
So
nice, nice.
yeah,
Yeah, David Mackay. Yeah, he was just in the
yeah,
same meeting that I was in. He's great. He's great.
yeah.
That's cool. That's cool.
Absolutely. It was a lot of fun. It was the first time I did a live coding thing, and he made it super easy.
Yeah.
Yeah.
No, he's a pro. He's really really good at what he does. Yeah, they were talking about other stuff that's going to be going on with cloud native TV. They're starting to do some new things.
Oh, nice.
They'll Yeah, that'll be launching in June. So yeah. Anyway, as we are getting people to start showing up, we got our YouTube stream going now. All right, we're already getting some nice feedback. Hey, that's good. So yeah, so we are, we can start, because it is 9 o'clock here in California, meaning it is 1 p.m. in New York. I always get mixed up with is it 12 or 1? What time is it in New York?
It's 12.
Perfect. Good. All right. Hi, everybody. Welcome to another meetup of the Data on Kubernetes community. As always, it's a pleasure to be here. My name is Bart Farrell. I have the good fortune of being able to host this meetup today with Matt, who's going to be telling us a lot about a lot of different things, which is why I want to get into this quickly. Having said that, I am going to leave one link. I promise not to spam anybody too much. I am going to leave a link because you can win some. DoK swag. We've got t-shirts. Your t-shirt is on its way, by the way, Matt.
Great.
But if you want to win DoK swag, but more importantly, to help us improve as a community, we're going to be taking some big steps in the next few weeks. So get ready for a lot of announcements about new things that are going to be happening. But in order to do that better, we need your feedback. All right. So I'm going to leave this here in Zoom and also on YouTube. Please fill out the survey. Please fill out the survey and give us your feedback. All right. So that we can take that into account as we move forward, as we continue to grow as a community, to know what kind of meetups you want, what kind of content you want to see. I guarantee we will have Matt back by the time 2021 finishes. We were also talking about KubeCon. We will be active in KubeCon just as we were in the previous KubeCon. So keep your eyes open for that too, because we'll be making some moves there. That being said, we were just talking before we got started. Postgres is a hot topic, and it creates controversy. We get some healthy debates going. It's a very old database. It's been around for a long time. I'm coincidentally very close to Berkeley, California, where it originated in the 1980s. So that's exciting. I feel a special connection. But anyway, we're here today with Matt, this is definitely not the first time you're going to be talking about this topic, but addressing it from the angle of observability, thinking about Prometheus, talking about data on Kubernetes. Matt, welcome to the meetup. Thank you so much for joining us today. Can you just give a little bit of background about yourself? How did you get into the data world? Can you tell us a little bit about your academic experience as well too? Who are you?
Yeah. So it's kind of funny. I started off this journey, I guess, in academia, where I was working under a guy named Mike Friedman, who was my advisor at the time, and I was working on this crazy idea for the time of how do you do data analysis of data across continents. And that was a bit early. It was really meant for somebody of like Google's scale and how do you handle transfer, because a lot of people don't know, but actually intercontinental data transfer is significantly slower and significantly more expensive. So anyway, that's where I met Mike, who's the CTO of Timescale. He was my advisor, and actually, um, all of kind of the founding engineers were in that same research group, and we just came up with the Timescale. So I'm in this really kind of strange for technology situation where I've worked for the same people for over a decade, which is kind of interesting. The same core team, if you will. But after I did my research, we started working on Timescale, which I'll tell you about in this talk. And then I personally kind of went more in the Prometheus and Promscale direction and started applying TimescaleDB, which is our database, to the observability space. And the reason I did that is because I really believe that our approach is a little bit unique in that it allows you to go from observation to understanding. And we'll get a little bit into the how and why of that.
All right. That being said, just as a quick reminder for some of the folks that are just arriving, this is your time to engage with Matt as much as you want. Leave your questions in the chat. You can do it either on YouTube, you can do it here in Zoom, you can do it in our Slack, you can do it on Twitter. He's already said that he will stop anytime there's a question. So feel free to jump in. We want this to be as dynamic as possible, get as much interaction as possible. That being said, Matt, all yours.
Great. So who am I? I live in New York City. I'm the tech lead of Promscale. You guys can connect with me on Twitter or on the DoK community Slack, as well as the TimescaleDB Slack. Personally, I enjoy geeking out about skiing, theater, travel, and photography. And given that this is 2021, I haven't really been doing much of any of those, so happy to chat with people about that anytime. Cool. So let me start off by telling you a little bit about what Promscale is. Promscale is an open source long-term store for Prometheus data, and it's built on top of TimescaleDB, which is a PostgreSQL extension. And what really sets us apart in this space is that we are the only observability data store which is built on top of a relational database. And that really gives you a lot about a lot of information, a lot of power to do analytics. Why did we choose Prometheus? Well, it's quickly becoming the industry data, the industry standard for collecting metrics data about your infrastructure and your applications. In my opinion, is becoming the industry data standard because the data layout and the data model is very easy to understand, and because of the power of PromQL, which is really a fantastic language for dashboarding and kind of SRE and the ops monitoring. And the second thing to know about Prometheus is it's really cloud friendly. A lot of the architectural decisions they made in the beginning, part of it is the pull model, other things as well. It's really built for a high dynamism environment like Kubernetes. So let me jump straight into the architecture to kind of give you a high level view of how all of this works. Prometheus collects data about your infrastructure by scraping targets within your Kubernetes environment. It then takes that collected data and uses what's called the remote write protocol to write that data to the Promscale connector, which does some processing and saves the data into TimescaleDB, which is again a Postgres database with TimescaleDB installed. It could be a single node or it could be a horizontally distributed architecture. On the query side, you can query that data using either SQL, using any tool that speaks SQL, Tableau, etc., or you could query the connector directly using PromQL, and you could use tools like Grafana or PromLens for that. At this point, you might be giving me the side eye because why would you ever store high velocity time series observability data in the relational databases. Relational databases are not really traditionally known for scale, and you might be saying this is a little bit crazy. And if we were talking just about Postgres, you'd have at least somewhat of a point. But TimescaleDB enhances Postgres to allow it to scale to hundreds of billions of metrics on a single node. It adds really best-in-class columnar time series compression algorithms, including Gorilla, which a lot of people know from Facebook, but also Delta Delta and the other specialized time series compression algorithms, which are really optimized for this type of a use case. And it is also horizontally scalable. So we do have a multi-node version that allows you to scale. But it's one thing for me to tell you this, and another thing for me to show you how we've achieved all this. So let me give you a really high level overview. Well, the reason that traditionally RDBMS don't scale is because the main workhorse indexing data structure in an RDBMS is really the Btree. It's the thing that relational databases have used since the 1970s to optimize finding stuff on, back then it was spinning disk. But what's also known about the relational databases is they don't really handle high velocity data ingest. And the underlying reason of that is that once Btrees themselves get bigger than memory, once a Btree cannot be memory collocated, ingest slows down. And this might be okay for transactional workloads because there's a certain type of Btree localization there. But for time series data, it really causes a problem. And let me kind of try to show you why this happens. Just a reminder, Btree is this kind of sorted tree data structure. So in this example, the root has items 1, 10, and 20, which means all of the children will start at either 1 or 10 or 20 and go from 1 to 10, 10 to 20, 20 to infinity. It's this kind of sorting thing that you have. And let's say we're inserting 3 things, 8, 17, and 5. And because I'm showing the case where Btree can't fit in memory, you can only fit 2 of these nodes in memory at a time. So let's say we're inserting the number 5. To insert 5, we have to kind of traverse the path in the tree to the point where 5 will be placed. So in this case, we will load into memory the root and the leftmost node, and we will modify the leftmost node to insert the 5. So that's all good and well, but now we want to insert 17, and 17 will go into the middle node. But we don't have the memory capacity to ingest, to put the middle node into memory, right? So what we do instead is we have to evict a node. We would evict the leftmost node, causing it to write to disk, and then load up the middle node, and then say 17. Now, in order to insert the 8 again, we have to do the reverse. We have to write out the middle node and load in the leftmost node again. So now we've just inserted 3 things, and we've done, I think, 6 I/O operations, 2 of which are really small writes to disk. This is not I/O efficient at all. And so again, to reiterate, the challenge here is that we are writing to random parts of the Btree. Let me stop there. The data we are inserting is actually time ordered. So you might think that it would be co-located to a certain section of the Btree. But the fact is that often what we want to search for in these in this kind of data is we want to search by another dimension. So by device or by series ID in the observability space. So that really becomes the prefix of the B tree. And now, even though you're time ordered, uh, you are still writing to random parts of the B tree because yes, you're writing to the latest uh, time, but you're writing to different devices or different series, and so you're going to be writing to completely random parts of the B tree. And as the table grows large, and this index no longer fits in memory, you're going to cause random writes and a lot of swapping. So this is the challenge with a relational database. Now I'm gonna go a little bit into how we fix that. And to show you this, let me kind of show you data in the graphical format. So we have data coming from different places, different devices, different series, doesn't matter, over time, right? And one trick we can play here is we can partition this data by time. So your recent data uh, comes into one-time partition, and your older data gets put into other partitions. And you can kind of specify these partitions either manually or automatically. For Promscale, this all happens automatically for you. Um, but in addition to partitioning by time, you can also partition by what we call space, which means by, again, by device ID or series ID. And now each kind of box in this multidimensional space becomes what we call a chunk. Um, People who are familiar with Postgres might think of it as a inherited table. It's kind of a subtable of of an overall bigger structure. But the important part to realize here is that the B tree is now defined locally on that subtable and not globally over your entire data set. And so what happens is that we could now right size these chunks. We could size these chunks in such a way that chunks corresponding to the most recent time where you are actively writing things is now small enough that all of the B trees for that chunk fit in memory. And so these older chunks don't really matter because you're not writing as often to them. The high velocity data goes to the most recent chunks. And for those chunks, all of your indexing structures will not fit in memory just because of how we size these partitions. So that's how we solve the kind of big problems with ingest that the relational databases typically had. But this kind of chunking also gives us other advantages. One of them is now we actually reuse the same structure for compression. What we do is we compress only the older chunks. This gives us a lot of advantages because,
Real quick,
yeah,
I got a question. Someone just kind of playing devil's advocate wants to know if we're talking about non-relational databases, Cassandra, Cockroach, etc. What kind of differences might or challenges might just quickly would you think would be in those kind of cases?
yeah. So the workhorse of those databases is called an LSM, a log structured merge tree. And those is a very different structure than a B tree. You could think of a B tree as kind of indexing on data time. In a way, a log structured merge tree indexes on insert time. It creates a kind of indexing structure corresponding to when something was inserted. And then you kind of have to go back through history of all of your structured merge trees to find stuff, and they have compaction to solve that. But it was invented kind of to solve the same problem of co-locating everything that's ingested recently into one structure. But in my opinion, the fact that you have to kind of traverse several structures back to find anything makes the querying a bit less efficient. So we have one Btree, which is canonical for any time period. In an LSM, you will have 3 or 4 merge trees that are canonical for any time period that you have to traverse back across, if that makes any sense. So they solved the same fundamental problem in a different way in a solution that has different trade-offs.
Okay, perfect. Thank you.
Yeah. So getting back to compression, since compressing older chunks has several advantages. One of them is that because you are compressing one chunk at a time and the chunk already has a lot of data, your compression actually works better. Because to a first approximation, compression works better the more data you have, because if you will, it could do more analysis and kind of find more commonalities with the data, the more data it has. So that's one. The second thing is that on the query side, this is kind of a hybrid system where you have recent chunks that are uncompressed and older chunks that are compressed works very well. Because what we find is that the kind of queries that people do on the recent data are really kind of more like debugging queries. Something really went wrong, right? Something broke in your system, and now you know kind of very fine-grained parameters about what broke, and you're trying to dig into very niche specifics. And so you actually want stuff in uncompressed form where the B trees are very specific to specific rows to access those fine-grained queries. However, as data ages, you're usually not doing fine-grained analysis. You're doing roll-ups or aggregates over longer periods of time. And here, actually having stuff in compressed form is better, because the compressed form is more like a columnar format in columnar databases. And the one thing that columnar formats are really known for is the ability to do very fast rollups and aggregates. And so this kind of a hybrid model gets you kind of the best of both worlds. The other thing that we use partitioning for is horizontal scale-out. Since we have partitioning even on a single node, for us it was very natural to just take those partitions and spread them across nodes in your cluster, right? Horizontally. And because they were partitioned already on time and on device ID, we could do a lot of query optimizations, including kind of push downs of aggregates and push downs of limits, and make the query over the horizontally scalable system much more efficient. Okay, so hopefully I've kind of convinced you that this is now possible, but sorry, one thing I didn't mention is that this all happens automatically under the hood, or there's partitioning, or there's writing to partitions. So you as the user don't have to worry about it. But now that I've kind of mentioned why this is possible to do, let's go back to the question of why is this even a good idea? And if we go back to our architecture diagram, the reason this is really a good idea is because now you have flexibility in how you query the data that you have in your database. So if you see in this architecture diagram, you could query data in both PromQL and SQL. Let me concentrate on SQL because that's really the unique part about the system. No other long-term software Prometheus data really supports full SQL queries. And what SQL allows you to do is much more in-depth analytics about your observability data, right? Um, SQL is actually a Turing complete language, so at least theoretically you could do arbitrary logic in it. But let me give you some specific examples of where this is needed. The first example shows you fine-grained aggregation control. So let's say we want to get the median request latency over your app version, right? So this kind of analysis is useful if you want to see as your versions kind of evolved, what happened to the median of the request latency, right? And this might seem like a very straightforward query, but that's actually not a query that PromQL can give you exactly, because PromQL always aggregates over a particular series first, and then you could do other aggregations on top of it. But a specific app version ID may have many series, so you have to do some kind of aggregation by series and by app version. And if you do this kind of two-level aggregation, a median of a median is not the same thing as a median. So if you're doing this kind of very careful statistical analysis, this is something that you just cannot do in PromQL. The other thing that's kind of also related to aggregation is rollups and cubes. In your like analytical analysis, you might want to like get the full matrix of your request latency by app version ID and the rollout ID to see how each affected the other. And SQL allows you to get this matrix back, which gives you the latency for each combination of app version ID and the rollout ID, as well as app version ID across all the rollouts and vice versa. So you get this kind of complex matrix very efficiently. The third thing that the SQL gives is it gives you fine-grained security control. So Postgres supports a role-based access control model. Which means you could really control the security, and Promscale provides a lot of roles that are easy to manage and kind of tailor-made for the observability use case. A fourth reason is join. So PromQL allows you to join things between different observability data, but you might also want to join things across observability data and relational data. So let me give you an example. If you have a system where, for example, you've collected a lot of information about your machines, for example, the type of hardware, the types of CPUs, the type of memory, the model of the CPU or hard disk, the size of your volumes, all of this information, right? And you ingest this into a relational table in your database. It's now very easy to then combine information about your usage with the type of CPU to, for example, compare AMD chipsets versus Intel chipsets or something like this, right? That's a very powerful feature you'll hear me mention a few times in this talk. And then, there's a lot of statistical functions in SQL, and you could also write your own. Let me give you one really cool example that we came up with, and this is really inspired by a post by Dan Liu about using observability data to kind of get real world benefits for your company. This, I understand this query is a little bit of a monster, but the first part of this query, what it does is it collects, it kind of takes your containers, and for each container, it figures out how much memory you're allowed to use according to the spec. And the second part of this query is it takes the amount of memory actually used by your container and finds the percentage of memory used by memory allowed and finds the 99th percentile of that. And so the result here will be by container giving you the percentage of memory used as a percentage of the memory provisioned. And what happens here is if your 99th percentile of that percentile of that ratio is very small, say less than 1% or less than 5%, you know that you've over provisioned that container, which means that you can decrease the amount of memory you provisioned and at the end of the day save your company a lot of money. So this is the kind of analysis that's really enabled by having a relational data store back up your um, observability data. I should mention at this point that timescale is,
Sorry.
yeah.
Disadvantages of using SQL that you would, I mean, just quickly might identify.
Sure. Let me go to this query. This query is very
Then
long.
like you said, the monster query. That's one.
Right? It's not the prettiest thing to write, and so the thing I would say is like when using Promscale, you don't have to choose. You don't have to choose SQL over PromQL. You get both, and you get both in an efficient manner. And that's because we really believe that there are a whole lot of queries. I would even say most queries that are better run on PromQL because it's easier to write is a shorter query. But man, when you have to do in-depth analytics, nothing beats SQL, in my opinion at least.
Okay. What do you have to deal with? That's a good quote. We'll use that for Twitter.
So you saw that monster query on the last slide. One of the reasons the query is such a monster is because there are not a lot of analytical functions really geared to time series analysis. And we have a project in Timescale to kind of fix that. It's an early project. A lot of the stuff is still experimental, but we've added a lot of very interesting analytical features to Timescale that you can use in your SQL queries. Just to give you some examples, there's graphing libraries or graphing algorithms like ASAP smoothing or LTTB, which is least triangles, 3 buckets, I think, or something like that. But the basic idea is if you have a lot of data points and you want to graph all of them, you don't want to be using JavaScript to graph a billion data points in your browser. It's going to crash. So what everybody in the space does is it takes a billion data points and compresses it or lowers the amount of data points by sampling or something to give you less points, and the idea is to use less points but give you a good graphical representation of what's going on. And so random sampling is actually not the best here because you have a random chance of seeing an outlier, right? And so ASAP, both ASAP smoothing and LTTB are ways of sampling those points, if you would, to preserve the overall shape of the graph and to give you a good visual representation of what's going on. In addition, we have a lot of approximates of things like count distincts and percentile approximations that are really algorithms that are proven to give you approximations of a statistical guarantees. So even if you are analyzing data over years, right, with trillions of points in there, you really often don't want to be doing a scan of all those points. And so you want to use some kind of approximates. And this allows you to use approximates that are kind of pre-materialized without losing all control over the fidelity of the data. So I talked a little bit about SQL. Now, what are the other advantages of relational databases? Well, one of the major advantages is support for a flexible data model. Most Prometheus, I want to say all other Prometheus long-term data stores only support storing floats. But in timescale, just as in Postgres, you can store float strings, bools, GPS coordinates, IP addresses, custom types, right? So you have a lot more flexibility in what you're storing. You can also use either a narrow or wide model. And this power really comes with the joins, because then you could join all of these different types of data together and with your metrics data to do correlations, to do metadata enhancement, which is the example I gave you before, where you join CPU information with machine information about the CPU, and you can even combine that with business data as well. There are other advantages, including the ability to use sugars constraints, user-defined functions, and transactions that are kind of more important for advanced use cases. And the flexibility in data models really goes to Promscale's vision, which is a flexible database for Prometheus and the other observability data. And what do we mean by flexible? Well, we mean several things. We want the flexibility to both pull and push data. We want to be able to ingest data in different formats. The Prometheus remote write protocol, JSON data, the Prometheus text protocol, other data formats, for instance. We want, I've covered this ad nauseum by now, we want both PromQL and SQL. We want to be able to not just ingest data that's for the most current time period, but we want to be able to backfill our data, which is super important if you're migrating between different systems, right? Or if you have, say, devices that could be offline for a while, and then you want to ingest their data later on. We want the flexibility in data types, and I think most interestingly and most kind of pie in the sky is different data modalities or different signals. So right now, we support ingesting metrics through Prometheus, but this flexibility also will allow us to ingest logs, traces, events, for example, Kubernetes events, etc., etc. And so the ultimate vision is kind of one database to rule them all, where you ingest all of these different types of data into Promscale together. And this has several advantages. One major advantage, I think, is ease of use and operations. So databases, I'll be honest, they're hard to run. It's fundamentally, they're hard to run, and there's only so much you can do to make them easier to run because they deal with state, and fundamentally, state is hard. Once you have a state, you need to do backups. Once you have state, high availability and failover is really, really tricky. That's not to mention the other kind of usual operational headaches that you have, which is security as well as scaling and tuning your databases. And let me tell you, as a database vendor, you're always going to need to tune your database. It's always going to be hard to scale and tune your database to a certain extent, just because people have different data models, they have different data SKUs, and there is a fundamentally hard problem that will always involve some degree of tuning. And so the question is, why do you want to deal with this multiple times? Why not just use one database where you can develop a common set of expertise to deal with all of these issues? And I will say here that even if you decide that you don't want to store, let's say, logs and metrics in the same database instance, you might, there's still major advantages to storing it in different instances, but the same type of database. Because again, all of your runbooks, all of your ways of dealing with data recovery, of dealing with things that go wrong, they will build up expertise in one area, which you can reuse over and over and over again. The second reason why I use one database is, of course, yeah.
Question, because you mentioned, the challenges of databases, challenge of working with state. In your experience, and particularly that's something that comes up a lot in Kubernetes, and maybe this is something you're going to comment on later, but someone asked, is regarding the stateful, stateless debate. Where do you stand on that, or what's your experience been?
I mean, stateless is always better. Is always easy to work with, but a database to a state, you cannot get away from that, right?
Yeah.
So sure, make everything that you can stateless, but at the end of the day, that only makes your database more important. There's just simply no way of getting around the complexity of state in a database. And I will cover, by the way, in the end, having a relational database actually allows you to make more other parts of your stack stateless. I'll go into that in a little bit.
Good.
Yeah. Cool. So yeah. So again, common query languages, and again, joins between these different types of things. For example, you can create types of pseudo metrics from your logs and your traces, which then you can combine with metrics or vice versa. For example, you can measure how often you have a log line with a particular terminate or whatnot, and make that into a count and the rate. And there's just, this is a case where I truly believe that the sum of the parts is greater than the sum of the individuals. So however that saying goes. Cool. So now let me switch tacks a little bit and talk about the observability stack for Kubernetes, which is our way of installing Prometheus and Promscale and this whole assortment of tools in your Kubernetes stack. So we looked at this and we saw how people were deploying observability today, and we thought, oh wow, this is hard. It's hard because you have to pick all of your components. You have to pick your collection component, your graphing component, your remote storage component, right? There's all of these components, and it's really an alphabet soup at this point to some extent. And for people just getting started and just wanting to get a basic monitoring or observability stack up, this is very difficult. After you pick your components, you still have to figure out how to connect them together using Kubernetes services or whatnot. And then there's security, networking, backups. It's really difficult. So what we built is we built Tabs, which is a Helm chart combined with a CLI tool that's very opinionated. It's opinionated out of the box, but also customizable. So we pick the components for you, but you can then choose to swap components in and out as you will. And this allows people to get started much quicker. So the kind of components we picked out of the box is a collection of tools called Prometheus, which contains Prometheus, that contains alert manager, which allows you to do alerts on top of your metrics. It includes node exporter, which exposes node data about your machines to Prometheus. The Prometheus operator, which like does hot loading of changes to your Prometheus config, and kubestate metrics, which exposes Kubernetes state changes as metrics in Prometheus again. So that suite of tools, and I forgot Grafana on there. That Grafana allows Prometheus to collect a whole lot of data about your Kubernetes infrastructure. To that, we add Promscale and TimescaleDB and automatically connect a Prometheus to write data into Promscale and TimescaleDB, as well as Promlens, which is this great UI tool to allow you to help you build PromQL queries in a intuitive and user-friendly way. And if any of you are kind of PromQL novices, or even not novices, and are having trouble figuring out an exact PromQL query, I highly recommend Promlens for that. So the basic architecture looks something like this. There's Prometheus, which I described, which scrapes your Kubernetes API server, as well as all of the other services in your Kubernetes environment. And then all of this is connected to Promscale and TimescaleDB for data storage. Now, this is where I will mention stateless versus stateful services. Usually when you deploy Grafana, with a state. There's a PVC attached to Grafana that stores the configuration data that Grafana uses to store your safe dashboards and other state like this. But Grafana also has a plugin to, instead of storing that state on a file system, store that state in a relational database, including Postgres. And so what we do here is we move this state that Grafana has into the TimescaleDB or Postgres database as well. And so now your Grafana pod becomes stateless. And so you're kind of putting all your seeds in one basket, which means it's important to have that properly backed up and maintained. And if you want, Timescale has a cloud SaaS service called Timescale Forge to help you do that. But at least you don't need to do that multiple times, right? But the Tubs CLI doesn't just stop at installing. It has a suite of commands to help you manage the life cycle of the stack. So you can do things like get passwords and change passwords. You could expand the volumes used to store your data. You can put forward everything. You can set configuration options. For example, on your metrics, you might want to change the retention period of either the default retention period of all your metrics, or we also allow you to set the retention period on a per metric basis, which is kind of a unique feature in the space, and stuff like that. And we will be adding more and more kind of commands to help you really manage this infrastructure in a much simpler way. Yeah, and that's kind of the end of my talk. You can get more information about tabs on links or go to our Promscale GitHub page, which has a lot of information on there, including links to our design docs, which show you how we design the relational schemas to store all of this data. Or you can just talk to us. We have a Calendly link. You can schedule some meetings for us to talk with you as well.
Perfect. I also linked the GitHub repo for PromLens in the chat. But a question that we got from somebody, without getting into too many details about how old we are, I'll break the ice. And I'm 35. So, but in your case, when did you first start working with databases? How many years ago?
I'm actually also old. I'm a 38. So I actually, my first job out of college was a full stack development. So that was back in 2005. So yeah. I've been using databases, and I made the mistake of starting out with MySQL, but then quickly moved to Postgres.
You corrected that, yeah. Had an iteration, and moved over.
Okay. Yes, I've been 15 years.
Okay, so a fair amount of experience. I think we can agree on that, because the question is kind of going with this, and also it's interesting. In the beginning you mentioned interest in traveling, right? So if we're thinking about databases as sort of trip or voyage that we're all on together, from the things that you're seeing now, the things that you're working on, things that are happening. Once again, the reason why Data on Kubernetes, the community, exists is because of this sort of new frontier where things are going. From what you can tell, what's going on right now, where do you see things in the next few years? What are the changes that you think that, because it's something we talk a lot about in our community as well, DBA to SRE, that sort of journey. Observability is a huge component for SRE. So based on the stuff that you're seeing now, what kind of changes do you think folks should keep in mind?
So first, let me talk to what I think is really the interaction between databases and Kubernetes. I'm actually a firm believer in all of these moves to create operators for databases. I think this kind of automatic lifecycle management, automatic failover, automatic backups, all of this kind of stuff is it's not an improvement, it's a step change. It's going to lead to a fundamental difference in how we think of and interact with the databases. I said before that databases are hard to manage, but they're getting easier. I don't ever believe that we'll get to a point that it will be as easy as a stateless service, but it's gonna keep on getting better. And it's gonna keep on getting better because of Kubernetes and um, or or things like Kubernetes and the operators, where all of this is in code and in kind of things. So I think the role of the DBA, at least when I started working, when I was a full stack engineer, let me tell you,
In
we
2000,
did
in 2005.
2005, so maybe not that long ago, but we did schema design, we did, figuring out how to ingest the database, and we also did like making sure the database is running and making sure backups is happening. Right? We did it all. And I think uh, the best DBA will tell you that the really fun stuff is the schema design part and the kind of index design part and figuring out how all of this will will work together to give you the best performance. The the SRE upkeep backup stuff was always a chore. And I think that's going to keep on getting better. And so DBA um, will be able to work more on the fun stuff than the non-fun stuff in the future. And yeah, I think that's super exciting.
Yeah, that is, and like you said, is that I think it's still very much in the initial phases, and that's one of the
Yeah,
reasons why I think operators, relieve a lot of the stress and pain points that a lot of DBAs and SREs are going through, which
yeah.
is why it's something that we've talked about on more than one occasion, all the different operators. And then comes the question, as you said, one database to rule them all. Could there be one operator to rule them all in the future? That's something that's been proposed a couple of times. Any thoughts on that?
Yeah, I don't believe that.
That's what that's a simple answer.
Yeah. And I'll explain why. The more and more you get into databases, the more you understand that there are very real trade-offs that people make and very different design decisions that people make.
Hmm.
And so I did say one database to rule them all, but it's really one observability database combined with a relational database to rule them all. I don't, for example, fully believe that uh, graphing databases will really become part of this,
Mhm.
or some other kind of specialized databases. So I don't, just because of the trade-offs people make, I think on the operations side as well, those design decisions will kind of bubble up, and you are gonna have to make different design decisions in how you operate and automate the database. And so I think, there'll be one operator for Postgres, but there might be a completely different operator for Mongo, right? A
Yeah.
document database is very different.
And that and
Um,
that's and that seems to be generally
yeah,
the answer that we've got, is that, like you said,
yeah,
is that it just kind of, tailor it to those specific
yeah.
situations, and rather than thinking about something that's going to be able to encompass everything. So anyway, I think it's a fair statement. That being
The
said, go ahead. Yeah.
Yeah, I was gonna say the other thing you think you asked about trends I see in databases. Kind of not in Kubernetes, but a trend I firmly believe is gonna continue going is data is gonna keep on getting more voluminous, and the velocity is gonna increase. I fully believe that you know the stuff you can get out of the data is just so powerful that people are going to want more and more granular data and
Yep.
more data over time. And I will go so far as to say that the more often that happens, the more often you're going to get time series data as opposed to other kinds of data. So we're going to see a move from other kinds of data to time series data because people are just going to want to track all changes over time.
Like you said, the value there is so strong. And that's an interesting thing for our community as well, too, because a lot of it's talking about, what's the problem here? But what are the opportunities? And I think that's a really good point that you're mentioning about granular data. And also, as you mentioned, the volume, we're just talking, just more and more and more. We had, it's even problems for data centers or just the amount that those are growing at a very, very rapid pace. That being said, I think it's a great way to finish. I just have one question. Can you stop sharing your screen so I can share mine really quickly?
Yes.
Okay, because we have a tradition. Very, very good. We have a tradition in our community. As you were while we were listening to you, can you see my screen now?
Yes.
Good. So we have our graphic recorder, Angel, who's absolutely amazing. So while you were talking, he created this graphic description of, or visualization, we could say, of all the different topics that were mentioned. Obviously, we would need quite a few drawings to probably get to everything, but I think it's a nice summary. It was, I said in the beginning, and I'm going to repeat it now, Matt, we're definitely going to have you back in 2021. I'm thinking some kind of a panel would be really, really good to get you debating, interacting with some other folks that we've had, talking about Postgres, talking about the challenges that you mentioned, that monstrous query that we saw. I don't think we've ever had a more monstrous one in our meetups. So that we established a very high standard for complex queries that we'll always be using from now on. Like, did you see Matt's talk? But anyway, I think you made it very clear. The documentation's open. If folks want to take that further, we can continue the conversation in Slack. Matt, thank you very much for your time today. And to all the people that attended, thank you for your questions. You can fill out our community survey to win some swag, win a hoodie, win a t-shirt. Matt, any closing remarks you'd like to make?
No, I'd like to thank you. You run a great meetup here. I'm happy to participate in any way. I actually love panels. So
good. We'll do it. We just got to pick a date. So everybody keep that in your radar. We'll have something planned in the next couple